Assalamu alaikum. Today we'll be discussing chapter number 1 from the book Electric Fundamental Circuits from Alexander and Sadiku. This book is very important and very good in its contents. We'll review the basic slides and solve some problem and discuss the basic idea about this course. So, electric circuit analysis is a basic course. Let's start with a good prayer. So, as you know, that electricity is the most important parameter that the modern worlds run upon, and you can see these circuits everywhere. The difference between electrical and electronics is that electrical is basically used for the transmission of electrons, whereas electronics is used for controlling the fine elements, mostly in DC. So, as the modern world progresses, these are used widely in both areas. So, we have a series connection and we have a parallel connection. So, if the loads, there are two primary sources. One is the source, like the battery is the source, and one is the load. These bulbs basically present a load, and this is the equivalent circuit. You can see this symbolizes for the battery, and these are the loads. So this is basically a series circuit. You can see all the things are basically connected in a similar line, and the second circuit you can see is basically a parallel circuit, and this circuit represents the battery, and these two loads depicting these bulbs are basically connected in parallel. You can see these are connected in parallel, and even if one bulb fails, the second bulb will complete the circuit. In order for this circuit to run, the loop must be completed. So if a bulb is basically fused or destroyed, this basically series circuit will be broken and will not be completed. Hence, this circuit will not work. So analysis of circuits is very important when we basically want to design these elements, and the designing is important because we want to control the flow of electrons, and these electrons can be seen with the help of advanced tools like oscilloscopes. You can design their movements, plan their movements, and then observe using the semiconductors that we'll be discussing in later part of the course. And these are available in all the particular areas. So modern trains are powered by electric motors, and their electrical systems are best analyzed using AC or phasor analysis techniques. Knowledge of circuit analysis enable oneself to use circuit simulator developed for students to learn analog and digital power electronics. So these are important part that can come in later part of your degree programs. And then we have different types of elements, like this is basically a transformer. The point of showing these components here is that you will often see these components in your circuits, and you need to relate the symbols used in the calculations. So here we represent the transformer, which basically converts, usually used for step down and step up. So if you provide a high voltage like 220 volts AC, this can be converted to 12 volt AC by this component, which is called transformer. And then particularly loads are used after different types of circuits involved. So knowledge of circuit analysis help to analyze any electrical device with their equivalent circuit representation. This circuit is used to represent the transformer. So motor is a very important component. You can see equivalent representation of this motor in the form of an inductor, the resistor, and different types of field resistors and armature resistors are depicted in this diagram, which represents this motor. So you see chargers everywhere. Chargers are the most important component of modern digital life, and there is a huge pack of components that are packed in a very small area. And modern chargers are very intelligent chargers, and they use different circuitry to give a stabilized DC voltage for our mobile devices like laptops, our mobile phones, and etc. And the internal circuitry uses different types of capacitors, inductors, AC, DC bridges. Different components are used to basically convert the AC, usually the line voltage that comes in Pakistan and different types of Asian countries, is basically 220 volts AC, and the mobile usually used 5-volt DC, and this DC is a straight line. So if you go in Europe and different US type countries, they used 110 volts AC, and that 110 volts AC works on 60 hertz. In Pakistan we use 50 hertz. So the circuit basically works. Usually these circuits work for both. The ratings is basically written from 110 volts to 220 volts onward. So again, this is again a component that can be represented. Bridge rectifier, very important component. And then we can have different types of circuits, DC to DC step converter circuits. Then we can just say that if we have a parallel circuit, if a single circuit is a break, the loop stays completed. So the rest of the lights basically will work. But if we have a series circuit and a single bulb is basically broken, all the chain will be incomplete, and the circuit will not work. So usually we can represent series circuits and parallel connections in this form. You can easily see that if one part is disconnected, the loop will not complete. However, if any of these lamps doesn't work, the circuit will still continue to work with the other lamps. So linear circuit analysis form basics for many subsequent electrical engineering courses, and the study of course electronics relies on the analysis of circuits with devices known as diode, transistors, which are used to construct power supplies, amplifier, and digital circuits. This will come in later part of the your degree programs, but again these are the foundation. This course is basically the foundation for the coming courses, and the skill which we develop are typically applied in rapid methodological fashion by electronic engineers to design and develop circuits. So we'll learn the basics in this circuit basic linear circuit analysis course, and these will basically be in first part will be focusing on the DC side. A DC side basically works, you can see the battery is basically a DC source, a voltage source, and then this is a load. Electric circuit is a connection of electrical elements, and we have a battery, we have a load lamp, and then we have these conductors, the copper conductors that carry the voltage through the load, and then the load basically utilizes that battery source. A good example is given for an electric circuit for a radio receiver. It uses many components. The point of basically showing these type of circuit is to make a higher level aspects that what we are looking for in future. Hopefully we'll be designing such circuits in later courses, but the fundamentals will be discussed in this course. Like we have like resistors here, like we have inductors here, we have capacitors here, and then specific type of components like crystals that provide oscillations, transistors. You will be seeing them in the form of dependent voltage and current sources. And then we have like op amps and battery symbols and grounds, variable capacitors. So basically you will be seeing these different types of symbols that basically represents a circuit, and engineering notations are universal. It does not depend that whether you speak some particular language. to understand engineering. Engineering has its own language, and this language is represented by the symbols that we'll be learning throughout this course. And if you see a circuit designed by anybody using standard symbols, irrespective of their language, you can understand what they are trying to say. So in first chapter, we'll be focusing on the concepts like basic concepts, system of units, electric charge, current, voltage, power, and energy, and circuit elements, and we'll see what these are. So basically the units that are used to quantify different standard things are length, mass, time, electric current, thermodynamic temperature, luminous intensity. And the basic units are like for length, if you want to measure length for a particular rope, you can use this length, and its basic unit is meter, and symbol is used is m. Notations are important. And then if you want to take some particular mass, you can use the notation kg, and basic unit is kilogram. Time, very important, second, basic unit, and symbol is s. Electric current, amperes, a. And then thermodynamic temperature, Kelvin, K. And then we can have specific like Fahrenheit temperature and centigrade temperature. They are like derived from this basic Kelvin, and they are for better understanding of human criteria. But Kelvin is a standard temperature unit. And then we have luminosity with candela, CT is represented by this thing. So derived units again are coulomb, volts, ohm, important, very important, coulomb, volt, ohm, Siemens, Henry, for capacitance, farad, for frequency, hertz, for force, Newton, energy and work, joule, power is in watt, and then magnetic flux is WB, Weber, and Tesla is T. And when you want to quantify these units, you will use these SI units to represent how much these numbers represent. So like 10 raised to power 9 is giga, mega, kilo is like 10 raised to power 3, and then centi is 10 raised to power 2, milli is 10 raised to power minus 3. So we can say that 1000 milli basically seconds, 1000 milliseconds represent 1 second. 1000 milliseconds, 1k milliseconds represent 1 second. So kilo will cancel with milli, 10 raised to power minus 3 will cancel with 10 raised to power 3, and we have 1 second. So we can say that 1 millisecond is 1,000th of a second, and like 1 micro is like 10 raised to power 6. So approximately you can say in our unit 1,100,000 of a second if we use micro as a unit. So these are standard units that help us simplify the notation, because the values are too big. So if you don't use these notations, then SI units, then our calculation can be exhaustive, and we can do errors. So better it is that we properly use these notifications. So charge is an electrical property of atomic particle which matter consists, measured in coulombs. The charge E on the electron is negative and equal magnitude of 1.602 into 10 to the power minus 19 coulomb, which is called electronic charge. The charge that occur in nature is integral multiple of the electronic charge, and this means that if we say 1 ampere current passes through a wire, that is approximately 6.24 billion electron per second flows, and this is represented by 1 ampere of charge. So if you want to quantify electric current, so this is basically dq by dt, and the unit of amperes can be 1 ampere, 1 coulomb divided by 1 second, and dq divided by dt is represented by this I, and I is the current that a load requires to run properly. So if we want to find Q, we can say I is equal to I into dt is equal to dq, and if we apply integrations on both sides, this will be cancelled and will end up Q is equal to I dt, and will define the limits for the interval for which we want to find this rate of change of charge with respect to time. So a direct current that remain constant with time, this is a DC current, and alternative current is a current that varies with time, alternate or reversed its direction from the positive to negative side and then negative to positive side. This cycle is completed. Usually AC voltage is used when we want to transmit electricity from longer areas. The AC basically voltage helps us travel more with less losses. However, with DC current there are losses, and hence usually for transmission purpose we use alternative current rather than DC. So electron charge 1.602 into 10 raised to power minus 19 coulomb. So 1 ampere can be defined with 6.24 into 10 raised to power 18 electrons per second. So the direction of current flows electric current due to flow of electronic charge in a conductor. So there is a conventional current and there is an electron current, and these conventions are used. So conductor has a 5 ampere constant current of 5 ampere. How many electron pass a fixed point on time on the conductor in 1 minute? So you can say the total number of charges passes in 1 minute. 1 minute is equal to 60 seconds. So we can just multiply this thing. So in particular 1 minute, 5 ampere current will travel with 300 coulombs per minute. And if we want to find how much total number of electron that pass in 1 minute, we can divide it with 1.602 into 10 to the power minus 19. So approximately 1.87 into 10 to the power 21 electrons per minute will pass. So the second numerical says the total charge entering a terminal is given by Q is equal to 5t sine 4 pi t millicoulombs. Calculate the current at t is equal to 0.5 second. So if we want to find charge entering a terminal, we can find the current by using this equation, I is equal to dq by dt. So if we want to find this particular current, we'll derivate it with respect to time, and we'll apply the multiplication rule here. So we have this like 5t and sine 4 pi t, differentiating, taking this term as constant and doing this thing with d by dt of 5t. We have 5 sine 4 pi t plus, then we'll take 5t as constant and take sine 4 pi t derivative, which will be cos 4 pi t into 4. So that 5 multiplied by 4 is going to be 20 pi t cos 4 pi t, and then we'll submit this value of t is equal to 0.5 wherever we have this variable t. So t 0.5 means 1 divided by 2, so this will be 2 pi, and again this will be 2 pi as well, and here this will be t divided by 2 to 10. So we can have this term, and the current is basically 31.42 milliampere. Voltage or electromotive force is the potential energy, is the energy required to move a unit charge through an element measured in volts, and we can calculate VAB is equal to dW by dQ. W is the energy in joule and Q is charge in coulomb. Electric voltage VAB is always across the circuit element between 2 points in circuits. VAB greater than 0 means that potential A is higher, whereas if VAB is less than 0, it means that A is lower than the potential at P point. The voltage is a very important parameter, and we can take the analogy with respect to a pipe. The voltage between 2 points is analogous to the change in height between 2 points in a pipe. And taking the hydraulic analogy, voltage is analogous to height in gravitational field. The higher the water is, the more the potential energy it has. So usually if you see that in your homes, when water is less, then you can feel that the flow coming from the tap is lower, and you can predict that the energy or the water in above tanky has reduced, and you need to run the water motor again. So same is the case with the charge stored in a battery. If you are running a toy car and your voltage is low, you can feel that the car or the motors are not moving according to the speed that was required to be. So water is flowing through the pipe. There is a height difference across these pipes, and we can extend a two pipe analogy. The diagram is intended to show a water pipe that breaks into two parts and then combines again. The size of the blue arrows are intended to reflect the amount of water flow at the point. So if we have different pipe lengths, the pressure will remain the same, and flow rate in the smaller pipe is less than it is in the larger pipe. And it's similar if we have like a resistance, then this voltage in that particular resistance will be going accordingly, because this smaller pipe particularly gives a specific type of a resistance, and this larger pipe will give a different type of resistance. Here the flow is easy, and here the flow is little bit harder because the pipe is smaller. So no matter which path you follow, the height is the same across the two pipes, and the height does not depend on the path. The height between the 2 points does not change as you go through the pipes. Only this pipe will give different type of resistance to the water. So talking about polarities are going to be the reference point through which you will be taking this flow of current, and this is an important point. It is extremely important that we know the polarity or the sign of the voltage and current we use, which way is the current flowing, where is the potential higher. To keep the track of these things, two concepts are used: reference polarities and actual polarities. So power is the time rate of expanding or absorbing energy measured in watts, and if we have a like dW by dt, we can basically break it like dW by dq and dq by dt. Dq by dt represents I, and dW by dq represents V. So if the power is going from positive to negative, if the current is flowing from the positive side to negative side, we call that this is power is being absorbed, and we can use the positive sign. And if the current is going from the negative side to the positive side, we'll say that we are supplying the power, and then we'll choose a negative sign with that particular power. So you can see, calculate the power supplied or absorbed in each case. So if the power, the current direction is going from positive to negative, you can see that this is basically power absorbed, and same is the case here. The power is going from positive to negative, the current is going from positive to negative, so this is power absorbed. And if it's going from negative to positive, then this is basically power supplied. So you need to follow the direction of the current to find whether it's power supplied or if power absorbed. If it's power supplied, then you will add a negative sign, and if it's power absorbed, then we'll have a positive sign associated with it. Law of conservation of energy. The total power will be algebraic sum of all the powers in the circuit will be equal to 0. Energy is the capacity to do work measured in joules, and we can get the work by integrating power with respect to a specific time interval, and 1 watt hour is equal to 3600 joules. So find the power delivered to an element at t is equal to 3 millisecond if the current is entering its positive terminal is given by this thing, and there are two parts of this numerical. One is v is equal to 3i, and the second is v is equal to 3 di by dt. So if v is equal to 3i is given and we want to find the power, power is equal to vi, and v is basically 3i, and I is also given. So the equation is 3i square. So if we put the value of v is equal to 3i as given here, it becomes 3i square. So 3i square, this will, we can take the square, so this becomes approximately 25, and then we have cos square 60 pi t. So, and then we multiply it with 3, this becomes 75 cos square 60 pi t. And if we put t is equal to 3 millisecond in this, we can get the answer. So this is like at t is equal to 3 millisecond, 75 cos square 60 pi, and we put t is equal to 3 millisecond, and we get this answer 53.48 watt. So we'll also use calculator to see how to get this answer. So we'll if we are using the calculator and we want to use the value of pi, we can just write the equation as such. So we can write it like 75 cos square 0.81 pi. So like 75, put it like 75, and then we have cos 0.18 pi, take it square, we get this 53.48 watt answer. And similarly, if we take the derivative of I, so this will be minus 900 pi sine 6 pi t, and then when we get p is equal to vi, we can get the particular answer by solving this equation, and we'll get this answer 63.96 kilowatt. We'll also calculate this answer. It requires that you brush your skills for derivation and then take your calculator and substitute these values accordingly. So we have taken our calculator in radian. You can go by doing this thing, shift, then press mode, and then take it to 4. This takes the calculator in mode of radian, where you can basically put the values of pi directly. So the value is minus 4500, shift and pi, then it is sine 0.18 pi, brackets closed, then it is cos 0.18 pi. So the answer is minus 6395. You can say minus 6.395 kilowatt. And alternatively, you can solve it in degrees as well. So next we have different types of active and passive sources. An active element is capable of generating energy, while passive element is not. Generators and batteries are example of active elements, while resistor, capacitor, inductors are passive elements. An ideal independent voltage source is an active element that provides a specified voltage or current that completely independent of the circuit elements. And an ideal dependent source or controlled source is an active element in which source quantity is controlled by another voltage or current. We'll see some examples related to it. So electrical source is a device that is capable of converting non-electric energy to electric energy and vice versa. A discharged battery converts chemical energy to electric energy, whereas battery is being charged converts electric energy to chemical energy. And a dynamo is a machine that converts mechanical energy to electrical energy and vice versa. If operating in the mechanical to electrical mode, it is called generator. If transforming from electrical to mechanical, it is referred to as motor. So an ideal voltage source is a circuit element that maintains a prescribed voltage source in its terminal regardless of the current flowing in those terminals. And an ideal current source is a circuit element that maintains a prescribed current through its terminal regardless of the voltage across its terminal. So basically both symbols A and B can be used to represent our DC voltage source, while A is used for time varying independent voltage source. Typically independent constant current source is shown in figure below. Dependent sources are useful in modeling elements such as transistors, operation amplifier, and dedicated circuits. Example of current controlled voltage source is shown in the right hand side of the figure. The voltage source depends on the current I through the element C. So you can see this is a voltage dependent voltage source, and this is controlled by this scaling factor of 10I, and the I current is basically the current that is going from here. So this I current is basically controlling this voltage source. So this is basically a current controlled voltage source. This is a independent voltage source, and this is basically a current controlled voltage source. Example of a current controlled voltage source is shown in the right hand side of the figure. So active elements like we have this voltage controlled source, and then we have this dependent voltage control source. This is a current controlled current source. This is a current controlled current source. This is basically independent, and this is dependent. This is a resistor. There are three elements that are particularly used in circuit analysis. One is the resistor, one is the inductor, and one is the capacitor. So a dependent source is an active element in which source quantity is controlled by another voltage or current. So these are like dependent sources. This is a dependent current source, and this is a dependent voltage source. And these are like round are independent voltage source and independent current source. This is shown by these arrows, and they have four different types, and we can say voltage controlled voltage source, current controlled voltage source, voltage controlled current source, and current controlled current source. Keep in mind the signs of the independent sources as well. So like these are the four variables: voltage controlled voltage source, current controlled voltage source, voltage controlled current source, and current controlled current source. So obtain the voltage V in the branch shown for I is equal to I2 is equal to 1 ampere. So let's say this I2 is equal to 1 ampere. So this Vx will be 15 into 1. It will become 15 volts. And then we have 10 volts. And if we want the polarity, keeping this, we want the voltage, keeping these two reference. So these two voltages will be added, and we'll have approximately, now we'll have 25 volts. We'll have 25 volts. So basically this is just a function of some other variables that will be described in the circuit. So 15 I2, and this I2 here is 1 ampere. So this is basically a function, this dependent voltage source, and this is controlled by this current. So you can say that this is a current controlled voltage source, and the current is 1 ampere. The law of conservation of energy. Energy is the capacity to do work measured in joules, and we have seen this W is equal to P di by dt, and 1 watt hour is equal to 3600 joules. We have seen this thing. Now we'll try to calculate this example, and we can see that this current is coming from this side and entering from the negative side to positive, and 20 multiplied by the current is 5 ampere. So this will become 100 watt. Sign is important. So minus is the sign, minus 100 watt. Then this current enters this from the positive side. So this becomes 60, 12 5s are 60, P is equal to VI, and with a positive sign. Then we have this thing, the circuit suggests that 6 ampere current is going from this positive terminal, and this becomes 48, 6 8s are 48 from the positive side, so we'll say that 48 watt. And then we have this current 0.2 I. This I is basically function which is controlled by this I. These are, look for the values. So this I is basically a function. This is a current controlled current source 0.2 I, and this will be multiplied by this 5. So we can have, particularly speaking, we can multiply this thing and get the values. So to get the power, 8 is equal to 0.2 I. 8, the voltage will remain the same. Whatever voltage is here, this is 8 volts here, and this 8 volt will also be same as it is parallel to this current source. So we can have the 8 volts here as well. So when we multiply this thing, P is equal to VI, P is equal to VI. So 8 into 0.2 I, and this I is basically as opposed to this current, this is opposite, and since that for reason we use the negative sign. For P4 we should note that the voltage is 8 volt, positive at the top, the same as the voltage for P3, since both the passive elements and the dependent source are connected to the same terminal. And remember that voltage is always measured across an element in a circuit. Since the current flows out of the positive terminal, and so this is basically taken as negative with negative sign. So you can see that because the current is technically speaking going from this side, negative side, to positive side. If you take, because the voltage here is in this same polarity, if it is coming in this aspect, and the current, we can see that the current is going in this direction. So you can see the current is going in this direction, and we can say that the current is with the negative polarity, and we can hence write a negative sign to it, and this will be a supplied voltage. Now we'll add the positive and negative supplies. So minus 100 plus 60 plus 48 and minus 8, this equals to 0, which proves law of conservation of energy. And this is in some books it refers to as Telegan's theorem. And this overall sum should be 0. So you can try some other circuits for your own practice. These are from book exercises as well, and some from practice problem. Do try these problems. And then we have the application of these electron beams in TV pictures carries 10 to the power 15 electrons per second, and these are electron guns. And then we have vertical deflection plate and we have horizontal deflection plate. And when this these basically the charge passes, the deflection is dependent upon how much do we have here on the vertical and horizontal plates. The old TVs use these technologies, and old monitors use these technologies. Now this is replaced by LEDs and LCDs. So in another example, we'll try to calculate and compute the energy that is being utilized in our homes. So typical average monthly consumption of household is given. We may be asked to calculate the total bills depending upon specific tariffs. So a homeowner consumes 400 kilowatt hour in January. Determine the electricity bill for the month using the following residential rate schedule. So base monthly charges are $12. First 100 kilowatts per month at 16 kilowatt per hour. Next 200 kilowatt hour per month at 10 cents, and then so on. So you can see that you can compute the values. Base value is like these are fixed charges, and then for if we have used 400 kilowatts per hour for the first 100 kilowatts, it will be charged with 0.6 kilowatt per hour. For the next 200 kilowatt, it is going to be charged with 20, and for the remaining it will be charged with 0.06. So this is the total amount that is charged, and with the total units we have used are 400. So 13.5 cents per kilowatt hour is the value. So carefully when we are solving the circuits, we'll apply specific techniques. We'll carefully observe the circuit, and will present everything is to be presented about the problem, like what is in series, what is in parallel, and then establish a set of alternative solution and determine the one that promises the greatest likelihood of success. Attempt the problem solution, evaluate the solution and check for accuracy. Has the problem been solved satisfactorily? If so, present the solution. If not, return to step 3 and continue to the process again. Like just assume that this is a problem and we want to find out the unknown currents and voltages. Let's say to solve for I8 ohm using mesh analysis will require writing two simultaneous equations to find the two loop currents indicated in figure 1.2.1, and you'll use nodal analysis, which requires solving for only one unknown equation. This is the easiest approach. So we can define these nodes and we can write equations according to these loops. We'll define the different currents. So we can say that I8 ohm, the current that is following that is passing through this 8 ohm resistance. Now we can name it with I2, and we stand here. I2 will be the voltage that is basically between a higher voltage and the ground voltage. Consider this is the 0 volt. So V1 minus 0 volt divided by 8, and I8 ohm can be represented as V1 divided by 8. So if we apply a nodal analysis, we can say that the I1, I2 and I3 is equal to 0. So this is current I1 V1. The current I1 is basically V1 minus 5 divided by 2. So this current is I1. This is represented by this equation. We know that V is equal to IR and I is equal to V divided by R, and V is the reference voltage between a higher potential and a lower potential. Considering that this is a higher potential, so we say that V is equal to V1 minus 5 divided by this R 2 ohm. Then the second voltage is V1 minus into minus 3 divided by 4. So this equation I3 is basically relating to this thing, V1 minus into minus 3 divided by 4. And lastly V1 minus 0 divided by 8. So we can take the LCM and compute these equations and solve for value for V1. When we solve for value for V1, we get this particular equation, and after solving that, V1 comes out to be 2 volt plus 2 volt. We can substitute this value into our equation, which was V1 minus 0 divided by 8, and hence we can get the I8 ohm is equal to 0.25 ampere. So this is one of the solutions that we can get, and we can confirm this answer and evaluate the solution and check for the accuracy. We can now use the Kirchhoff voltage law to check the results that we have computed here. Now we know what V1 is and we know what I8 ohm or I2 is. So we can say that I1 was basically equal to V1 minus 5 divided by 2. So we can compute the value, place the value of 2. So this comes out to be minus 1.5 ampere. Secondly, we have computed I2 0.25 ampere here. And thirdly, we can compute I3. I3 is equal to, as we discussed earlier, V1 minus 3. Yani V1 minus into minus 3 becomes V1 plus 3 divided by 4. And this becomes, we know that V1 is equal to 2 volts, and we substitute this value, 1.25 ampere it becomes. So we accumulate all these according to Kirchhoff's current law, and that is basically we add all these things, minus 1.5 plus 0.25 plus 1.25, and the answer is 0, which proves Kirchhoff's current law as well. So this proves that our solution is calculated and it is okay. Now you can basically recompute this answer by using the KVL. So the KVL, Kirchhoff voltage law is applied. So this loop is taken as minus 5. You can see minus 5 plus V2 ohm, this V2 plus V8. So minus 5 plus V2 plus V8 equal to 0. We know minus 5. We know V2. V2 is basically I1 into R. So I1 is opposed to R loop because we are taking the loop in this direction. So we take this I1 with a negative sign and 2, and then we take this I2 with a positive sign because the direction of the current that we assume and the direction that is indicated are in same direction. So we can take this I2 as positive. So we calculate this thing, and the total sum of all the voltages around this loop 1 comes out to be 0. Similarly, if you apply the second loop 2 in this direction, you can see that this becomes minus V8 plus V4 minus V3 minus 3 volt equal to 0. So minus because the current direction of I2 is opposite, so we take a minus sign with I2, and then because I3 is sync with our direction, so we'll take that positive into 4, and then minus 3 volts, minus 3 sign here, and when we calculate it, it becomes 0 as well. So this is it. You can test these examples and then verify them, and you'll need to repeat them 1 or 2 times so that your confidence is up. So try the other examples, the practice problems, and good luck.